Wishing you all. I am Dr. J. Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the topic of light amplification and pumping mechanisms. So, in this session, we are going to see how the light is amplified, what are the conditions to get the amplified light. So that here in the previous sessions, we have seen that how laser is getting stimulated emissions. So because of that stimulated emission, how the light is amplifying like that. So here we are going to see the three conditions needed to amplify the light. Okay, and then we are going to see the pumping mechanisms. So here in this light amplification, the topics we are going to cover is photon density, population inversion, and then metastable state. So what is photon density and what is population inversion, and then what we call as a metastable states. So these three topics we are going to cover in this light amplifications. So to amplify the light, so first of all, we are going to see the introduction about this light amplification. So in this light amplification, so to amplify the light, amplify means that increasing. So to amplify the light, the medium we should have the following. The medium should have the following three conditions. What are the three conditions? Is large photon density, population inversion, and then metastable states. So Einstein's theory gives the necessary requirements for amplification of a laser light. Okay, so first of all, photon density. So the ratio of stimulated emission of radiation to spontaneous emission of radiation. So NST by NSP is equal to B21 N2Q divided by A21 N2. It is equal to B21 by A21 into Q. So the ratio, we are telling that the ratio of stimulated emission to spontaneous emission gives the photon density. So here the ratio of stimulated emission of radiation. So in the previous session we have seen that Einstein coefficients. So Einstein coefficients. So A21, B21. So or the Einstein's coefficients. Okay, so here NST, what we call as NST is number of stimulated emission of radiation. So number of stimulated emission of radiation, and here NSP is the number of spontaneous emission of radiation. Okay, so NST is the number of stimulated emission of radiation. And this NSP is the number of spontaneous emission of radiation. So the ratio of stimulated emission of radiation to the spontaneous emission of radiation gives B21 by A21 Q. So here the number of stimulated emission of radiation is equals to B21. Actually, NST will be B21 into Q. NSP is equals to A21 into N2. Why this number of spontaneous emission BA21 into is because this number of spontaneous emission of radiation do not depend upon the incident photon density. It does not depend upon the incident photon density. That's why A21 N2. So when we see the spontaneous emission, the atom is at the excited state A2. So in this spontaneous emission of radiation, after the lifetime of an atom, that is completion of 10 power minus 8 seconds, the atom itself transits to lower energy state. Lower energy state. So while it transits to lower energy state, it emits radiation. It emits radiation. This is called spontaneous emission of radiation. So spontaneously the atom transits to higher energy state to lower energy state by emitting photon. So this process is spontaneous emission of radiation. So the number of spontaneous emission of radiation do not depend upon the incident photon density, because there is no photon is interacting the higher energy state in the higher energy state atom, so that no instant photon is acting upon the atom which is in higher energy state. So that we are getting number of spontaneous emission of radiation NSP is equal to A21 into N2. N2 is number of atoms in the higher energy state, that is E2 state. That is at E2. At E2. A21 means that A21 is, so the transition comes from higher energy state A2 state to A1 state. So this is A21 is the Einstein's coefficient for the stimulated, Einstein coefficient for spontaneous emission. Einstein coefficient for spontaneous emission of radiation. A21 is Einstein's coefficient for spontaneous emission of radiation. Emission of radiation. Okay, so the number of spontaneous emission of radiation is equal to A21 N2. So it depends upon the number of transitions, depends upon the number of atoms in the higher energy state. So that NSP is equal to A21 into N2. Likewise, number of stimulated emission of radiation, NST. NST. So NST is number of stimulated emission of radiation. NST is equal to B21 into N2 into Q. So B21 is the Einstein's coefficient of spontaneous emission of radiation. N2 is number of atoms in the higher energy state. Q is the incident photon density. incident photon density. So we can recollect what is and the process of stimulated emission of radiation. So in the spontaneous emission of radiation, the atom in the excited state transits to lower energy state after the completion of 10 power minus 8 seconds. But whereas in the stimulated emission, the atom before the lifetime of an atom, the atom in the higher energy state is stimulated by some radiation, and before the lifetime of an atom it transits to lower energy state. So the atom is getting stimulated by photon, transits to lower energy state before the lifetime of an atom. So less than 10 power minus 8 seconds before the lifetime of an atom. The atom gets stimulated and transits to lower energy state by emitting some radiation. So here it emits some radiation and also it emits the incident photon radiation. So that this process is called the stimulated emission of radiation. So here in the number of stimulated emission of radiation, it depends upon the number of transitions and then number of atoms in the higher energy state and then incident photon density, number of incident photons. Okay, that's why number of stimulated emission of radiation is equal to V21 into Q. So when taking the ratio of stimulated emission to spontaneous emission, NST by NSP is equal to N2 will get cancelled. So V21Q by A21Q. So from this expression, the stimulated emission dominates the spontaneous emission if the density of the incident photon is very large. So if the incident photon density is very large, then the stimulated emission dominates the spontaneous emission. So more than the spontaneous emission, stimulated emission of radiation process takes place. Okay, so that if Q is very large, that is incident photon density is very large, then number of spontaneous emission of radiation will be less. Stimulated emission of radiation will be more. That's why. So from this expression we conclude that if the density of the incident photon is very large, stimulated emission dominates than the spontaneous emission of radiation. So thus, presence of a large number of photons in the active medium is required. So, however, it will lead to more absorption transitions. So, it has to absorb more to get a transitions. So, it will lead to more absorption transitions. So that a large photon density alone will not be sufficient for more stimulated emissions here. Next, coming to the population inversion. So, population inversion, in the way of expression, we can say The ratio of stimulated emissions to stimulated absorption is NST by NAB. So NST is equals to V21 into Q. Already we have seen in the photon density, right? So NAB, number of stimulated absorption of radiation. Number of stimulated absorption of radiation. So it is equals to V12 N1. So V12. So it is getting absorbed from first level to second excited level. So lower energy level to higher energy level. Transition from lower energy level to higher energy level. That is E1 to E2. N1 is the number of atoms in the lower energy state. Lower energy state. As you know that Q is the incident photon density. So when taking the ratio, so NST by NAB is equal to B21N2Q by B12N1Q. Because stimulated emission of radiation depends upon the incident photon density, and also absorption, number of stimulated absorption of radiation also depends upon the incident photon density. So after stimulating by the incident photon, the atom transits from lower energy state to higher energy state in the stimulated emission, stimulated absorption of radiation. So here, by absorbing some incident radiation, the atom getting stimulated within the lifetime, it transits to higher energy state to lower energy state is stimulated emission of radiation takes place. So here in this expression, taking V21 is equals to V12. So the number of transitions from higher to lower and then lower to higher. So V21 is equals to V12. Then both will be gets cancelled. So this will be cancelled. So NST by NAB is equal to N2 by N1. So this equation indicates that the stimulated emissions will dominate the absorption process if N2 is greater than N1. If N2 is greater than N1, then stimulated emissions will be dominate than the absorption process. So it means that there should be more atoms present in the higher energy level than lower energy level for stimulated emission to dominate over spontaneous emissions. So to achieve the number of atoms in the higher energy state is larger than the number of atoms in the lower energy state is called the population. Usually or generally, if E1 is the lower energy level, E2 is the higher energy level, and N1 is the number of atoms per unit volume in the energy level P1, N2 is the number of atoms per unit volume in the higher energy level. So here usually the atoms will be more in the lower energy state compared to the higher energy state. So to achieve, so here we have seen that in the equation 2, if N2 is greater than N1, here in this condition, general condition, here more number of atoms is in the lower energy state. So it means that N1 is greater than N2. So in this condition, N1 is greater than N2. Generally, so the condition the number of atoms in the lower energy state is greater than the higher energy state. But to achieve the stimulated emission of radiation be more, N2 should be greater than N1. N2 should be greater than N1. So if N2 is greater than 1, then stimulated emission of radiation will be more than the stimulated emission of absorption. So that's why we have to make it N2 is greater than N1. So N2 is greater than N1. Then only stimulated emission of radiation will be more. So if a stimulated emission of radiation will be more, then we'll get amplified light. So that we have to make this condition N2 is greater than N1. So means that in the way of diagram, we can see E1, E2, N1, N2. So wanted to make more number of atoms in the excited state. So here in this diagram, N2 is greater than N1. We have to make it. We have to bring to this condition. Then only we'll get stimulated emission of radiation more. So that to achieve this condition, that is to achieve more number of atoms in the higher energy state than the lower energy state is called the population inversion. So generally the atoms in the lower energy state will be more compared to the higher energy state. That is in this condition, N1 in this situation, N1 is greater than N2. But to achieve the get the stimulated emission of radiation be more, the number of atoms in the higher energy state should be more than the lower energy state. So to make this condition N2 is greater than N1, making N2 is greater than N1 is called the population inversion. So that's why to achieve the number of atoms in the higher energy state larger than the number of atoms in the lower energy state is called population inversion. Metastable state. A medium in which population inversion is achieved is called an active medium. So a medium in which population inversion is active. So where the population inversion is active, that medium is called active medium. So here in the equation 1, so in this equation 1, number of stimulated emission of radiation to number of spontaneous emission is equals to B21 Q by A21 indicates that stimulated transitions B dominate than the spontaneous transition if the ratio B21 by A21 is also large. So to increase the probability of stimulated emission, the lifetime 1 by A21 of atoms at the excited should be large. So the unit of A21 is second inverse. 1 by A21 represents the unit of time, which represents the lifetime of a excited state. So this is called metastable state. Atoms in the metastable state remain in the excited for an appreciable time. That time is in the order of 10 power minus 6 to 10 power minus 3 seconds. That is, before the lifetime of an atom, the atom gets stimulated by the instant photon and transits to lower energy state by emitting photon of radiation. So, atoms in the metastable state remains in the excited state for a appreciable time. So, the appreciable time is in the order of 10 power minus 6 seconds to 10 power minus 3 seconds. So, hence, the medium amplifies light only with the following three conditions, that is large photon density, population inversion, and then metastable states. So that Einstein's theory thus gives the requirements for light amplification in a laser source. So, we have seen here in this topic how the light is amplified in this laser. So, the light is amplified based on these three conditions. And then we shall move to the pumping mechanisms. So in the previous one, in the three conditions, that is large photon density, population inversion, metastable state. So here in the population inversion, usually N1 is greater than N2. We have to make this condition to N2 is greater than N1. To achieve N2 is greater than N2 is called the population inversion. So that is making more number of atoms into excited state. So here we are going to see, so making more number of atoms in the excited state will be done with the different mechanisms. So there are different mechanisms, different techniques to make more number of atoms in the excited state. So usually I told that usually in the lower energy state, atoms are more compared to the higher energy state. But to achieve the population inversion, we have to make more number of atoms in the higher energy state compared to the lower energy state. So to make this condition, there are different techniques. That techniques are optical pumping. So here we are going to see the optical pumping, electric discharge, inelastic atom collisions, chemical reaction, then direct conversion technique. So these are the topics we are going to cover in this session. So for laser action to take place, we need population inversion between the available energy levels of a system. So to obtain population inversion, the atoms in the lower energy level should be excited to higher energy level. So how it can be excited to the higher energy level from lower energy level is by supplying additional energy in the form of excitation mechanism. So we have to make a population inversion. So we have to invert the population of lower energy state. So that to make more number of atoms in the excited state, we need to supply some additional energy in the form of excitation mechanism. So what are the various excitation mechanisms we are used in this population inversion? So optical pumping. One of the technique is optical pumping. So in this optical pumping, we use a laser, we use a source of light to supply luminous energy to excite the atoms to higher energy levels to create population inversion for further laser emission of radiation. So in this technique, in this optical pumping technique, we use a light source to supply luminous energy. So by this luminous energy, the atoms get excited from the ground state to higher energy state so that the population inversion be created for the laser emission of radiation. So this type of pumping is widely used in the solid state lasers or ruby laser. The first solid state laser is ruby laser. So this type of pumping is known as optical pumping. Next, electric discharge. So in this method, atoms are excited by collisions with fast moving accelerated electrons in an electric discharge. So in this method, atoms are getting excited by the collisions with the fast moving accelerated electrons. So this mechanism is well suited for gaseous ion lasers. So best example is the argon ion laser. So the electric field between the cathode and anode of discharge tube causes the emitted electrons by the cathode to accelerate towards the anode. So these accelerated electrons collides with the gaseous atoms. So ionize the gas and raise them to higher energy levels, causing population inversion. So here we are using some electric field to make electrons to get accelerated so that the electrons moves fastly and collides with the gaseous atoms and ionize the gas and raise them to higher energy levels. So the electric field between the cathode and anode of discharge tube causes the emitted electrons by the cathode to be accelerated towards the anode. So these electrons collide with the gaseous atoms, ionize the gas and raise them to higher energy levels, causing the population inversion. And the next technique, inelastic atoms-atom collisions. So when the gaseous medium consists of two different atoms, then one atom is getting excited to the corresponding higher energy level by electric discharge. This excited atom collide with the different atoms in the medium inelastically, transferring its energy to its and pumping it to the equivalent its higher energy levels. So that population inversion is caused by the inelastic collisions between two various atoms of the gaseous medium. Like that, the atoms be excited to higher energy state so that we will achieve their population inversion. So in inelastic atoms-atom collisions, so we are taking a gaseous medium. In this, we are taking two different atoms. One atom is getting excited by the electric discharge. So this excited atom collide with the different atom in the medium and it transfers energy inelastically. It transfers energy inelastically to the other atom so inelastically transferring its energy to it and then pumping it to the equivalent higher energy levels. So that population inversion is caused by the inelastic collisions between the two different atoms of the gaseous medium. So this technique is mainly used in the helium-neon laser. Next, chemical reaction. So in this chemical reaction method, energy is released during the process of chemical method So in the chemical process method, the atoms get excited to higher energy level, causing population inversion in the lasing system. Okay, so in this, chemical energy is released. Chemical energy is released when the process of chemical reaction method. Okay, so in this method, the chemical energy released during the chemical process and get excite the atoms to higher energy level and causing the population inversion in the lasing system. So for example, hydrogen can react with fluorine. Hydrogen can react with the fluorine, so to produce the hydrogen fluoride. So in this chemical reaction, energy, that heat energy is liberated. So this heat energy will excite the atoms to higher energy levels. Like that, more number of atoms will transits to the higher energy level. So population inversion will be achieved in this chemical reaction method. So during the process of chemical method, then it produces some heat energy. So that heat energy excites the atom to transits higher energy levels. Next, direct conversion method. So when a PN junction diode is in forward bias, then recombination of electron hole pair across the junction emits some radiation. So in this process, the applied electric energy promotes the emission of radiation. Okay, so here in this method, PN junction, that is semiconductor we are using. So when a PN junction is in the forward bias, so when it is in the forward bias, so forward bias, PN junction forward bias means, so P type, N type materials, P type have more number of positive charge carriers, and N type more number of negative charge carriers, minor minority of electrons. That is in so P type and N type, here more number of holes. Here majority charge carriers are electrons. So in P type, majority charge carriers are holes. In N type, majority charge carriers are electrons. When we give forward bias, so the bias means that giving connection to the voltage battery. So P type will be given to positive terminal of the battery, and N type will be given to negative terminal of the battery. So this is in the condition of forward bias. So in this forward bias, when we giving forward bias, the P type semiconducting material having more number of holes, so that positive charge and here positive charge, they get repelled. So P type charge carriers repelled by the battery positive, so that P type majority charge carriers moves towards N type. Here in the same condition, so N type majority charge carriers or electrons, they get repelled negative charge from the battery, so that N type charge carriers moves towards the P type. So it get recombined here. So electron hole pair be recombined at this junction and emits some radiation. It emits some radiation. So in this process, the applied electric energy promotes the emission of radiation. So likewise, here we can pump the atoms, more number of atoms to the excited state. So the suitable example for this method is semiconductor lasers. So these are the different techniques we are using to achieve population inversion. So why we have to achieve population inversion means that to get a stimulated emission of radiation more, so that the light will amplify. So these are the topics which we are discussed in this session. So we shall see the next session. We shall see the other topic, which is lasing action, and then we shall go for Ruby laser and further. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.